Today we're doing practical 7. We're looking at the relationship between discharge and other parameters of water quality. We're doing this ultimately in order to be able to predict how water quality changes, and we've got measured water quality through a period, and we're going to use that to investigate the relationships between discharge and certain aspects of water quality, and by understanding those relationships we can try and predict how the water quality will change during the periods in which monitoring has not been carried out. The questions that we're going to address as a guide are, first of all, to look at the relationships between EC, electrical conductivity and discharge, and pH and discharge. So seeing how those change over time. And in order to do that, we just need to plot the time series data. So we can plot the discharge, the conductivity and the pH as a scatter plot. And because of the different values, we might choose to put the pH on secondary axis, and just move that out of the way. The next thing we wanted to consider was the relationship between solute concentration and discharge. Solute concentration being the electrical conductivity, that's the measurement of it in this case. In order to look at the relationship between the two of them, we plot one against the other. So the next thing to do then is to plot the discharge and the electrical conductivity against each other. Look at the relationship. Get rid of the title. So that's the relationship between solute concentration and discharge. So to examine the relationship between conductivity and discharge, we just select them and plot one against the other. So I'll do a scatter plot of conductivity against discharge. Get rid of the title. And we can add a trend line to see what the relationship is. Linear trend line, and put the equation and the R squared on the chart. Move that so we can see it. Okay, the R squared is very poor, and you can tell that there's a quite big scatter on those data points. So we need to think through now about the relationship, and how might we improve the relationship, and what does that tell us then about the processes that are actually going on. So if we consider the relationship between conductivity and discharge, by assuming that you've got a linear relationship, which is what we've drawn on here, we're assuming that the conductivity or the concentration will actually fall to zero, because if it's a straight line, then that straight line, if you extend it far enough, it will actually hit the axis here, which will mean that you've got a concentration of zero. And if we think that through, then that can't possibly be the case. no matter how much we dilute something, it won't completely disappear. So the relationship between conductivity and discharge, you can see from this observed data that it is a negative relationship, but it's not linear. You said, however much you keep on diluting concentration, it can't become zero, which is what a linear relationship would imply, as the trend line, if it's extrapolated, would eventually hit the axis and therefore would suggest that there's a concentration of zero, which can't happen. So we need to consider what is the mathematical form of dilution. What's the mathematical relationship for dilution? And it's going to be that the concentration is equal to 1 over the volume. In our case with flowing water, it's the concentration is equal to 1 over the discharge. So that's equivalent to the concentration equals discharge to the minus 1. So the straight line, if there is to be a straight line, would have to be of log data. If we take logs of both sides of concentration equals discharge to the minus 1, we get log concentration equals minus 1 times the log of discharge. So if we're to plot log concentration against log discharge, and then if we were to see a straight line, then that would imply that the relationship between concentration and discharge is purely one of dilution. So let's do that. Dilution is likely to be the dominant process, and that's why it's an appropriate thing to do, to make the data transformation into a double log plot, log concentration against log discharge. So log discharge, log concentration, and then if we plot these two against each other, we can get rid of the title, change these scales, make the minimum 1. Let's get that. It's better use of the graph. And then we want to add a trend line. Again, show the equation and the R squared. We can see whether we've improved the R squared. So the R squared is very slightly improved as we've gone from a plot of concentration against discharge to a plot of log concentration against log discharge, which is a better model for the actual physical process, because fitting a straight line to this data is never going to fit it, whereas there's a theoretical possibility it could fit here, assuming that dilution is a very important part of the process. Now, why then is the relationship still quite poor? Is there anything else that we could do to improve the relationship? Well, if we look at the scatter of points, is there anything that might be controlling the scatter? Well, one of the things we can do is connect the points together. If we connect the points together, it shows us the effect of time, because they're connected in time order. So rather than just being a scatter of points showing the relationship between concentration and discharge, we can also see the effect of time. And actually, it's not just a scatter. The data is actually a loop. And you could see it as more than one relationship. So there's a linear relationship here and a linear relationship here that changes over time. The points being connected in time order. It's known as a hysteresis. So it's a hysteresis loop. So time is a factor. We can understand this because the relationship between concentration and discharge is partly controlled by the availability of solute, and the availability of solute is going to be time dependent. If there's been a large discharge and therefore solute's been transported, the solute that's been transported isn't necessarily replaced by the time there's another large discharge, or should the large discharge continue, the rate that solute's removed at is greater than the rate it can be replaced. So over time there's a decrease in the availability of the solute, and therefore the relationship between discharge and solute concentration changes with time. So what we can do is split the data set into before and after the peak discharge. This is the discharge. We've got the discharge rising, and then we've got the discharge falling. So we could split the data set into the rising limb and the falling limb, and then see if the relationship between conductivity and discharge is better if we split it into these two. So two better relationships rather than one poor relationship, looking at the whole of the data set. So we can do that by take this up to, this is the rising limb, which you can look at on this graph. 88.07, which is here, that's the time. 88.07 is all the rising limb. So actually stand that down there. So that's the relationship on the rising limb, and actually you can see straight away we've got a very good R squared. We need to then redraw the graph for the falling limb. We can do that by copying the graph. We have the graph, but we need to change the data set to again, the R squared's better than it was, but the R squared's poorer for the falling limb than for the rising limb, but it's made a large difference in R squared for the overall. So we've got R squared of 0.9, 0.91 and 0.44 or 0.45. So that's a big improvement by splitting the data set. Can we improve the relationship any further? Well, the other thing to consider is the provenance of the solutes. We've got a measure of conductivity, which is a measure of all the dissolved soluble material. We've also got a measure of pH, which is a measure of one particular ion that's dissolved in the water, which is the hydrogen ion. And the total dissolved solids, or the conductivity, is material that's arrived from the catchment but also within the rain. Whereas the pH, the hydrogen ion concentration, is largely delivered in the rain. So the pH of rainfall is 5.65 because of the dissolution of the acid gas carbon dioxide into the water. So rain actually delivers hydrogen ion, it delivers a hydrogen ion flux, and the main source of the hydrogen ion in the stream is from the rain, whereas the total conductivity is made of the hydrogen ion plus all the other solutes. Those other solutes are typically those that have been dissolved in from the catchment. So what we can do is to separate this conductivity signal into solutes that have come from the rain and solutes that have come from the catchment. And that's a reasonable thing to do, because there is likely to be a dilution effect on solutes that have come from the catchment, but there's not going to be a dilution effect in solutes that arrive in the rain. The amount of hydrogen ion in the rain, which is there as a result of dissolution of carbon dioxide, isn't going to change according to the amount of rain that falls. It will be a constant pH. The pH of rainfall is 5.65, regardless really of how much rain there is. So separating the conductivity into its two components, which are a catchment related component, or largely catchment related, and a rainfall related component, should allow an improvement in the relationship between conductivity and discharge. So in order to do that, we need to first of all turn the pH into the hydrogen ion concentration. And that's done. The pH is the negative log of the hydrogen ion concentration. Therefore, in order to turn a pH into a concentration, we raise 10 to the power of the pH. These are very small numbers, so if we want to be able to see them, we should format them in scientific format. Okay, so the hydrogen ion concentration, if the pH is 5.73, 1.85 times 10 to the minus 6. Okay, so that's our hydrogen ion concentration. And we then need to turn the hydrogen ion concentration into its equivalent conductivity. So what's the conductivity that's produced by that amount of hydrogen ion? And then we can subtract that from the total conductivity, and then we'll have the two components of conductivity, the catchment related and the rainfall related. So the pH that's attributable to the amount of microsiemens that is attributable to the pH can be calculated if you know that the concentration of ions that give a particular conductivity, and the standard value that we use is that a conductivity of 1413 microsiemens is equivalent to 0.01 molar concentration. Now that's actually the concentration, 0.01 molar concentration of potassium chloride, but in this case we can take that as being its 0.01 molar concentration of any positive ion, in our case hydrogen ion. So we need to multiply our hydrogen ion concentration by 1413 times 100, and that gives us the number of microsiemens that we can attribute to the hydrogen ion component of the total dissolved solids or conductivity. We copy that down. So then we can also have the remaining conductivity, which is the conductivity minus the pH, and that's going to be equal to the overall conductivity minus the conductivity that's caused by the hydrogen ions. So it doesn't make much difference there, but the difference starts to get bigger as the pH actually decreases. When the pH is lower, there's more hydrogen ions, so it has more of an effect. So we can now plot, instead of plotting conductivity against discharge or log conductivity against discharge, we can plot the catchment related conductivity against discharge, which is what's in this column. Again, we need to take the log of this because it's appropriate to plot the log conductivity against discharge, and this is the log catchment conductivity. Again, with these we want to plot the log catchment conductivity against discharge, and we want to do that for the rising limb and for the falling limb. So for the rising limb, we're going down to row 14, applying that against the catchment related conductivity. For the falling limb, change these axes. We just want to add the trend lines, and we can see if we've improved the relationship. So we can see that the relationship is greatly improved on the rising limb. It's gone to 0.899, and on the falling limb it's much the same, I think. It's improved on the falling limb as well, but it's massively improved on the rising limb. It's gone from 0.44 to 0.89. So you've taken the data set and looked at the relationship between conductivity and discharge, and then by understanding the processes that actually go on in generating conductivity, you've improved the relationship by building those processes into your model. Now you need to draw these graphs out as a series of graphs and make sure they've got the correct headings on their axes, and they've got figure legends and figure numbers, and then use the relationships that you've established and the understanding of the processes in order to make some prediction about the impacts of increasing the acid burden into this catchment.